Welcome to this explainer. Today we're uncovering the invisible geometric blueprint that's literally hidden in plain sight all around us. Seriously, have you ever just looked around and realized that almost everything we interact with is built on a secret code of lines? We're talking intersecting lines, parallel lines, it's everywhere. So we're going to decode that structure right now. We'll unpack the geometry holding our world together, going from everyday objects straight into the precise mathematical rules that actually govern them.
Before we even touch the math, just look at this. Notice how piano keys are essentially just a structural pattern of parallel and intersecting lines. The keys themselves, they lie side by side, never crossing, while the edges of the piano cut right across them. So it's not just an instrument, it's a literal, living demonstration of geometry at work, creating harmony not just in sound, but in physical space.
Or take a look at this simple red bench. It's not just furniture, right? It's a strict grid of geometry that is literally keeping you from falling to the ground. Notice how the horizontal slats are perfectly aligned and the vertical supports cross right through them. If those angles were even slightly off, the whole structural integrity would completely collapse. So yeah, geometry is literally saving your tailbone right now.
And then you've got railway tracks. They perfectly illustrate the rules of structure and predictability that we are going to X-ray and understand today. Just think about it. If these two steel lines ever decided to meet or drift apart, it would be a complete catastrophic disaster. The entire system relies on absolute geometric consistency. So how exactly does this math actually work?
Well, here is our blueprint for today's explainer. First, the geometry around us. Second, what happens when lines collide. Third, the perfect right angle. Fourth, lines that never meet. Fifth, transversals and corresponding angles. And finally, creating your own lines. Let's jump right into it.
Section 1. The geometry around us, finding the plane. Okay, let's establish where these lines actually live. Because in geometry, lines don't just float around in a void. They exist on plane surfaces. Think of a plane as any perfectly flat surface that extends forever. The tabletop you might be sitting at, a bulletin board, or just a simple, crisp piece of paper. These are all snapshots of a plane surface. Every single rule we're about to discuss applies to lines that share the exact same plane.
Moving on to Section 2, when lines collide, or intersecting lines. Let's zoom into the micro level now and observe what happens when we take two straight lines on our plane and literally make them collide. In the real world, you'd call this a crossroads. But in geometry, we call this an intersection. So, ask yourself a couple crucial questions to unlock the geometry here. Exactly how many angles are formed in an intersection? And if you have two perfectly straight lines, could they ever possibly bend back and meet again at a second point? Take a second to just visualize that in your head.
The reality is, straight lines cross at exactly one point, and never again. When they do crash into each other, they form exactly four distinct corners, or angles. This simple four-cornered crossroads is honestly the foundation of almost all geometric logic.
Now what's really fascinating here is the predictable magic of what we call linear pairs. A linear pair consists of adjacent angles. That just means they sit right next to each other, nesting together to form one side of that intersection. And because they combine to form a perfectly flat, straight line right along the bottom edge, their measurements must always, without fail, add up to exactly 180 degrees.
So the absolute crucial point is this simple equation. Angle A plus angle B equals 180 degrees. Guys, this is basically your geometric superpower. It means if you know just one angle, you can immediately deduce its neighbor without ever reaching for a measuring tool. If someone tells you one angle is 120 degrees, you instantly know the one right next to it absolutely has to be 60 degrees. It's that simple.
But it gets even better. The angles opposite each other across the intersection, the ones staring directly at each other, those are called vertically opposite angles, and they perfectly mirror one another. They're absolutely equal. So if the top left is 120 degrees, the bottom right is also 120 degrees. This mathematical mirror effect, that's exactly how engineers ensure a massive skyscraper stands perfectly straight instead of leaning over.
Let's do a quick, fascinating reality check, though. It's super important to note the difference between ideal math and the physical world. See, in mathematical theory, a line has absolute zero thickness. It's a pure concept. But in our messy reality, when we draw with pencil lead or use a physical protractor, our lines have physical width, our hands shake a bit, right? We make slight measurement errors, and yet, the pure logical proof of the 180-degree straight line completely holds true, even when our real-world drawings are just slightly imperfect approximations.
All right, section 3, the perfect right angle, perpendicular intersections. So we know lines can cross at all sorts of skewed, slanted angles, forming wide and narrow corners. But there's one specific intersection that pretty much defines human architecture.
What do you think happens if you force an intersection where all four of those angles we just talked about are perfectly identical? We already know they have to add up in specific ways to form straight lines of 180 degrees, right? So if all four corners are exactly the same, what must their measurement be?
Well, if they're all equal, we just divide that 180-degree straight line perfectly in half. When all four angles are equal, they have to each be exactly 90 degrees. And this forms what we call perpendicular lines, a perfect right angle. It's literally the cornerstone of building walls, framing windows, and even creating the digital screens you are likely looking at right now.
Section 4. Lines that never meet. Welcome to the parallel world. We've talked about intersections, but what about lines that exist on the same plane surface but absolutely never cross paths? What if they just stretch on to infinity, side by side, without ever colliding?
Those are parallel lines. No matter how far we extend them at both ends, the gap between them never changes. This is that hidden structural backbone we saw in the artwork, the piano keys, and those train tracks from earlier. It's a beautifully simple concept, but it actually requires absolute precision to execute in the real world.
Let's move to Section 5, transversals and corresponding angles. Time to combine our concepts. Things get really interesting when a third line, which we call a transversal, slices right across a pair of those parallel lines. Imagine a street cutting diagonally across two parallel train tracks. That single slicing line creates an entire network of angles.
And this creates one of the absolute coolest tricks in geometry: corresponding angles. When that transversal slices through, it creates angles that sit in the exact same relative position at both intersections. Think of it like a geometric copy-paste. Because the two baselines are perfectly parallel, the angle created at the top intersection is perfectly equal to the corresponding angle at the bottom intersection. It's the identical math, just shifted down the page.
Finally, Section 6, creating your own lines, bringing math to reality. So, here's the crucial point. How do we actually construct these perfectly parallel lines when we're drafting a blueprint, or honestly, even just folding a piece of paper? We know the theory now, but how do we physically guarantee that two lines will never, ever meet?
We use the power of the 90-degree angle by intentionally drawing a baseline and then using a tool like a set square to draw two separate lines that are both precisely 90 degrees perpendicular to that same baseline. You mathematically guarantee those two new lines will be parallel. Because they share the exact same corresponding 90-degree angle, they are permanently locked into a parallel relationship.
You can actually prove this physically right now. No fancy drafting tools required. Just take a plain piece of square newspaper, make some horizontal creases, and then fold vertical creases right over them. You're physically creating perpendicular lines, and when you unfold it, boom, you are holding a perfect grid of parallel and perpendicular geometry right in your hands.
I'll leave you with this thought as we wrap things up today. Isn't it just incredible that by simply observing how imaginary lines intersect and by trusting these purely logical rules of angles and planes, human beings have managed to engineer, construct, and predict the entire modern world around us? Seriously, from the device you're holding to the building you're sitting in, it all starts with a simple straight line. But it really makes you wonder, what other invisible blueprints are dictating the world around you right now completely unnoticed? Thanks for joining me on this explainer, and keep an eye out for that hidden geometry all around you.